1. Okay. So today's Saturday session is on equilibrium and the fundamentals of equilibrium, and then a variety of aspects of equilibrium that you have to understand, SL and then HL. So the SL will be the first part, then HL will take about 20, 30 minutes to kind of talk about the difference in what you have to know for this. But so the real ideas that you really want to focus on is the concept of dynamic equilibrium, okay? And so there are a couple of things that we want to think about here when we describe this, okay? And so dynamic, meaning reactions are continuing. So that means that in this equilibrium state, there are still forward and reverse reactions that are going on constantly. And so there's always a constant exchange of reactants and products that are going on, right? Static would be the opposite. A static equilibrium is something where nothing's occurring. Kind of like if you have your laptop resting on a desk, it's in static equilibrium with the desk. It's no longer moving. The forces are equal. There's no motion. But in chemistry, everything is dynamic. Okay? Equilibrium has a couple of aspects. A closed system, meaning that it is sealed from the surroundings so that things can be constant, can reach an equilibrium. And the fact that the rate of the forward and reverse reactions are equal. That is the main definition of equilibrium. Now, there are things that can be observed when you reach equilibrium, but they're not part of the definition. And so equilibrium is based on, defined as rate, okay? The rate of the reaction is equal. So therefore, what that means is the exchange of reactants to products is the same rate as the products to reactants. And that's the main idea of equilibrium here, okay? And so, but things you'll see is when you reach equilibrium, no more color change, okay? The concentrations are constant. Notice I use the word constant and not equal, because you'll find that most equilibriums, the concentrations are not equal. There's usually favoring one side versus the other in the equilibrium. You may have more reactants, you may have more products, and that leads us to the equilibrium constant expression that we'll talk about later. Okay? And so these are the things in purple are things you might observe that are occurring in an equilibrium, but they're an effective equilibrium, not the definition of equilibrium. Okay, so it's whenever you're talking about, if you're stating explaining why a system's at equilibrium, you need to talk about the rate of the forward and reverse reactions are equal. Okay. Questions so far? Okay. Now, this kind of goes into a little bit from topic 6 and 16, which has to do rate of reaction, because in 6, you talk about graphing concentrations over time, and this is where you kind of get this graph that represents equilibrium. And so you may have a time on the X and a concentration on the Y. And let's say you start with 100% reactants and 0% products. In an equilibrium system, you're going to see the amount of reactants decrease and eventually level out. The amount of products increase and also level out. Okay. And we'll label this reaction R to P, just for simplification terms. Now notice there is a different arrow in here, the double arrow, that represents equilibrium, because this represents a reversible reaction, one that has the potential of going in both directions a non-negligible amount. Okay, so you'll see these double arrows, and so you'll see this applied later on in topic 8 when we talk about weak acids and weak bases. You'll see that they're reversible reactions as opposed to strong acids and strong bases that have single arrows. So it is important that you notice these differences in reactions. And if they ask you to write a reaction, you will need to include these equilibrium arrows as part of your reaction equation. You will lose points if you don't have it correct. Now, notice here that in this graph, you have concentration versus time. And so what you'll notice is the rate of our change is a slope at any given point. And so if you take the tangent line of any given point, you can find the slope of that change. Now, eventually, you get to the point where, let's see, it's not grade line, but let's just say here where they level out, where the concentrations become constant. That's because the rates are equal. And at this point, we would define this as having reached equilibrium, okay? And so if you're looking at the concentration graph where they become constant, where they become horizontal lines, that tells you that the rate is equal because you're producing the same amount of products from reactants as reactants from products. Now, the height at which the product and reactant lines are positioned at equilibrium, there's no fixed way. Sometimes the product line will be higher, sometimes the reactant line will be higher. But the fact that they're just constant is all that really matters. Okay. Okay. So you're literally looking at the point in this concentration versus time curve where they are equal and they're parallel to each other. That's where equilibrium is reached. And you can translate this into an additional graph, which relates to topic 6 as well, where you do, time and rate, okay? Now, the key difference here is that, like we said before, rate is equal at equilibrium. And so for the reactants, because you're using up the reactants, the rate will go down. And if you're using up if you're making products, the rate will go up. But then eventually they will be equivalent. And at that point is where equilibrium is defined. Now, the part before you can have as lines or curves, whatever way you want. All that you really care about is the fact that they are going to merge and become one line at the equilibrium. Okay. So the slopes and the shape of the line before it merges is really not super important. Like if the IB is grading you on sketching this graph, they're just like, does the student show that the rates are equivalent? That's what they're trying to show. Okay. But notice there are differences in these graphs here and how they look and how equilibrium position is determined based on these two graphs. Okay. Questions? Okay. Now, a couple of terms that you may see in the IB exam and in your text while you're studying. A homogeneous equilibrium is defined as an equilibrium of all one state, okay? Meaning one state of matter. So all gases are all aqueous, and so this simplifies equilibrium for us because we don't have other factors like solids and liquids being removed from the equation and things like that. So the IB is telling you that they're only going to do homogeneous equilibrium. So they're going to all be gases or they're going to all be aqueous in your problem here. And so what that means is that when you establish what we call the equilibrium constant expression, which we call K or KC here, The equilibrium constant expression represents the ratio of products to reactants at equilibrium. Now, that's not an actual like IB definition. You don't really have to define equilibrium constant expression, but I'm kind of telling you the way you want to think about it in if you're trying to understand the concept. So like that's not like a verbatim definition that you need to know. It's just that's the idea. And so what's nice is that when the IB does this, like we said before, they keep everything in the same state of matter. So like these would be all gases here. Because when you get into different states of matter, you omit certain states of matter and you from your expression and stuff like that. And the IB is not trying to complicate things further. But in college, you may run into that if you're doing equilibrium, that you have to omit solids and liquids, pure solids and pure liquids from your expression. Okay. And so if all these are gases, the expression for this is our products raised to their coefficient over the reactants multiplied together raised to their coefficients. And that is what the IB is asking for you when they say state the equilibrium constant expression. This expression right here. Remember, just like in math, an expression means no numbers. So you're not putting values of molarity in for NH3, N2, and H2. You're just literally writing them in variable form with their exponents. I guess the exponents don't really count as numbers because they're part of the equation, not like values that you're plugging in. So an expression in math is the same as expression in chemistry. No numbers involved. Okay. Questions? Okay. Now, that K value, like we said, is kind of a ratio of products to reactants. And what that means is your K value has kind of two major possibilities. It can be greater than 1, where it favors products at equilibrium, or less than 1, where it favors reactants at equilibrium. And what I mean by that is like the concentrations of those species at equilibrium. Okay, and so if you see a K greater than 1, you can fairly safely assume that you have a greater amount of products at equilibrium. And so the curve should have the concentration of products higher than the concentration of reactants at that. So like if we sketch it out really kind of small over here, you would see it as the reactants going down and the products going up. Whereas if K is less than 1, you would see the reactants higher than the products. So there's no requirement for an intersection in these equilibrium graphs. That intersection really only happens when the substance that you're starting none of with eclipses the amount the substance you're starting with. And you don't even have to start with all reactants. Is it the easiest way? Yes, starting with reactants, but conceivably you could start with all products and still have an equilibrium occur. So you don't have to just start with reactants. You could start with all products and you'd still reach the same equilibrium from either direction. Okay. And I think that's something that students kind of get confused about because they think, well, if the reaction is written this way, I can't start with all products. You can in an equilibrium problem because you're still going to have you're just going to have the reverse reaction happen first and then the forward reaction happen second. So it's okay to start with all products in these equilibrium reactions. So don't let that kind of make you question how to do these problems. Questions about that? Yes, Alistair. Yeah, in the IB it will not. So in the IB it will not have liquids mixed with gases. The only time I think that it might occur is in acid-base reactions where you have aqueous like reacting with water, but liquid water you always omit from your expression, so that's where it's safe. Yes. Yeah. Because this expression really only works for molarities, and pure substances don't have concentrations. They're a fixed amount. And so they don't, even if you add more of it into your problem, it actually isn't contributing to the state of equilibrium because the concentration doesn't change. So it's still the same concentration of solids and liquids that are in there. And so it doesn't actually affect the equilibrium. You're welcome. Other questions? Okay. Now, K is at equilibrium, but you can also use the expression to calculate when you're not at equilibrium, and that is Q, which we call the reaction quotient. Okay, so Q is essentially, like for lack of better terms, the equilibrium constant expression not at equilibrium. Okay, so it's the same exact expression, but now your values aren't at equilibrium. So what this does is it determines direction needed to reach equilibrium. And this is an SL and an HL idea of understanding which way is it going to have to shift to reach equilibrium. Now, it is an HL thing where you have to use Q to figure out which side that C is positive and which side the C is negative, but we'll talk about that when we get into the HL part. But here, we're just trying to figure out, okay, if Q is this and K is this, which way does the reaction have to reach? Because it's not at equilibrium yet. What is it going to take to get to equilibrium? Okay. So, for example, in this same equation up here, Q would still be equal to NH3 squared over N2 times H2 cubed. But what you do is you run into scenarios where you have to calculate these values. And so let's pretend we had the K of this reaction to be 20, for example. Okay. Now, if the K of this reaction is 20, and let's say you calculated Q to be 10, okay? Q is 10, K is 20. So Q is less than K currently, okay? So which way does the reaction have to shift to get to equilibrium? Okay, so looking at this expression, think about this. How do we make the number bigger to reach the K value? We have to make more products, correct. And so because the products are the numerator, you have to make the number bigger, so you have to take away reactants and make more products. And so you will shift to the products to increase this ratio. All of K is about this ratio. So if you really want to, like, remember one major thing is understanding that this is really products over reactants. That's the main idea of all of this, especially in SL, is that it's all about products over reactants and understanding what that means in K terms and what that means in Q terms. Okay. If Q is 30, Q is greater than K. So that means you have too much products, and so therefore you have to make more reactants. So this will shift to the reactants to reach equilibrium. And again, this is one of those things that you don't have to memorize these two ideas. Really, if you're doing the problem and you don't remember which way Q and K behave, just make up two fractions. Like you can literally see, like, well, if Q is 30 over 1 and K is 20 over 1, then to get to this point, I need to make this number smaller and this number bigger. And so that means I need to make more reactants. So I would encourage you not to necessarily remember Q is less than K, Q is greater than K, because in a worst case scenario, you can just plug in numbers and go, okay, what do I need to do to make this number go up or down? And that's one less thing you have to memorize. Okay. If you happen to know it, great. But again, this is all about minimizing what you have to memorize, because there is so much content you have to know, especially if you're higher level, like 21 topics worth of material, that anything that you can kind of figure out on the fly during the test by using a little bit of logic will save the memory space for stuff that's really crucial. As you probably learned, organic chemistry is a lot of memorization. And that is just one topic out of 21 for you high level students and one out of 11 for standard level students. And so, like, you're going to have scenarios on the IB exam where you don't remember completely what it is.
Right.
And it's how you deal with those problems and trying to logic things out is what kind of gets you up one grade boundary or gets you down one grade boundary. So it's about trying to problem solve during the test to kind of get kind of grab points wherever you can on a test, that even though you may not 100% understand the question and things like that. So it's all about kind of maximizing your points and stuff like that. So it's okay. Like, that's one of the mentality things that I have to, this is a little bit diversion, but that's one of the mentality things that I think students struggle with on the IB exam, is that they're used to getting every single question right on a normal unit exam. That's the expectation. You're supposed to try to get every single question right. But on the IB exam, you are going to run into questions that you don't know. And how you handle those questions and how you are able to kind of go past those questions or move on is going to help you maximize points. Because again, on the short answer, like, for higher level, it's 90 marks on the short answer. And to get a 7, it's 72 out of 90 marks. So that's 18 marks that you can afford to miss. That's like, I don't know, 5 to 9 questions that you could not know and answer everything else right, and you'd be okay. That is very different norm from a normal unit test, just because the quantity of the material is so much more drastically different. For standard level, it's 50 marks for short answer, but I think it's like 38 out of 50 is a 7. And so that means you have 12 marks you can afford. And so understanding, kind of getting that mentality is like, it's okay if I don't know this 1 mark question. I need to move on and not spend so much time on this 1 mark question because I have 50 total marks or 90 total marks to worry about. That's the mentality that we have to kind of work on. And you'll experience that on the mock exam. Everyone's going to feel like they failed the mock exam. Like, it's just so much material and it's just a very stressful situation. But then when you get your scores back and you see what your IB scores translate to, it will make you feel, hopefully, better than you felt when you left the mock exam. Hopefully. I mean, I don't think anyone's going to make a 1 or a 2 on this. But even then, like, I had a student make 2s on her mock exam. Like, she wasn't a 2 student. She was a very strong student, but there are a lot of factors that you can't factor in with mock exams and the stress of things like that. And like, it was a very difficult time and challenging time for her. And like, she still ended up overcoming that and made a 6 on the actual IB exam when it mattered, right? And so that's what she needed to get into university too. And so, like, there's a lot of extenuating factors in there, and so you try to do your best and you try to prepare as best you can. But even from mock exam to like actual IB exams, there's a lot of room for growth and a lot of time for you to kind of overcome the challenges that you have. And so, um, yeah, so you really have to kind of work about how to logic things out and minimize what you have to memorize. And that's the way I kind of teach things here is, hopefully this is one little detail that you don't need to memorize. You can just figure out if you need it in the problem. Okay. Questions about Q and K? Oh yeah, yeah. Shoot.
I feel like we've used before the shifting to the right or shifting to the left. Is that
The Chatelier principle.
oh,
Yeah,
okay, so that's the
correct. We are going to talk about that in a little bit. Okay. Now, for SL, you don't have to do a significant amount of rice charts here. With SL, most of the calculation, at least from what I'm looking at the syllabus here, is mostly about just solving for K already at equilibrium, or solving for one of the values at equilibrium already. So you'll be given K and some concentration and solve for the unknown concentration, or given all the concentrations and then solve for K given those values. So it's just a matter of being able to write the expression out and plugging numbers in. Yes, that is SL in some forms or another. Like, you don't have as really a lot of rice charts in SL. Like, not many at all I can think of. And so Um, but it is still an important skill that I felt like you had to have because some of y'all will end up doing stoichiometry as rice charts now that you've seen rice charts and do them. Because I'll spend a Saturday showing you, okay, there are a lot of different ways you can do stoichiometry, and a lot of people favor different ways. And you may find a way that you feel more comfortable with now than you did last year. Because the first thing you learn in a lot in the class is stoichiometry and stuff like that. And um, I think a lot of teachers tend to teach it one way and show you one way to do it and kind of make you do it that way. And it's not the best way for everyone. And so there's alternatives that might make you more successful in that calculation. We'll talk about that on a different Saturday. But yeah, SL is very math limited. Like the IB rationalized that SL chemistry is more conceptual, very less math forward. And so it's catered to students that aren't very math or science oriented but want to take chemistry because they're interested in it. So they remove a lot of the math from it. I know. And I think a lot of y'all here, the math isn't necessarily what's the challenging part of it. It's just the amount of material. And so, like, yeah, SL chemistry is very little math, but that also means that if you're a really strong math student, SL chemistry might be bad for you because all your skills in math are kind of wasted in SL chemistry, and so you'd have to know all the content really well to get the points. And some people don't memorize that well, but they can solve a problem, a math problem, um, like it's breathing. And so there's no, I wouldn't say that just because you make a 5 in HL, you're guaranteed a 6 or 7 SL because there's such a disparity between the content in those tests that I could have a kid make a 6 in HL and then a 5 in SL because maybe that kid's really good at calculating pHs, calculating rice charts, and calculating voltaic cells and stuff like that, and none of that is on the SL test. So they don't get any of the benefit of earning those points that they would normally get. So it's really tricky in chemistry as opposed to other sciences and stuff like that. Okay. All right. Oh, okay. So the last major idea for SL is Le Chatelier's principle. Okay. And the idea of Le Chatelier's principle is essentially an equilibrium um, responds to a stress to the system in a manner to restore equilibrium. Okay. And again, my definition for Le Chatelier's principle might vary from even from the notes from the very first unit we did here, but it's the same idea. You're never going to have to define Le Chatelier's principle. It's just I word it in a way that I think makes the most sense. And so it kind of varies. The exact vocabulary kind of varies from day to day, but it's still the same idea. You have an equilibrium, you do something to it by adding or taking something away, and the system, because it's closed, seeks out to restore its equilibrium. Okay. And so there's a variety of factors that can occur that affect how equilibriums are restored. Okay. So let's look at this equilibrium because I find that this is the best one to kind of use for our example here. Yeah. Now, the simplest thing you can do is add substances to the reaction. Okay. So you can either add or subtract an amount of substance. So, for example, if we add N2 here, okay, we are increasing this amount of N2. Okay. Essentially, what have we done now? We have too many reactants in our equilibrium. So what's going to happen to that equilibrium to restore equilibrium? It's going to have to shift, yes, Alexandra? To the right. Okay. It's going to shift to the right to increase the amount of NH3. But as a byproduct of that, Lucia, what happens to our H2 concentration? Right, because you have to consume some of the H2 to also go and make your products here. And so there's a shift to the right here in your reaction. Now, one thing I guess I should incorporate in here now that I'm looking at it is our delta H here. Okay, notice our delta H is negative 92. Okay, that represents what type of process here? Exothermic. So therefore, which side did the heat go on, Marina? Where does the heat go in the reaction? On the right. Excuse me, yes. So it's producing 92 kilojoules. So as a side effect of increasing the amount of N2, you'll also increase the amount of heat that's being produced as well. So the temperature should go up because it's producing more and more heat as the reaction goes toward that side of the equilibrium. Okay, so that is kind of a byproduct of things. So yes, understanding exothermic and endothermic is a prerequisite for parts of Le Chatelier's principle. Okay. Now, if you decrease NH3, now you have a deficiency in the product, so the reaction has to shift also still to the right to make up for that deficiency. And so your Q is changing in the manner that it's getting smaller because your numerator is getting smaller, so you have to make more numerator to return back to equilibrium. Yes, Andrew. Oh, because when you go to the right and you try to make up the NH3 that's being lost, you also make heat alongside it. So whenever you shift to a side, you make all those things. So even though you're taking out NH3 and you're making more of it, as a byproduct of that, you'll make more heat as well. Because every time you make 2 NH3, you make 92 kilojoules of heat. So the fact that it's shifting to the right means that you're going to increase the amount of both products. So you can never change, like when you're shifting, you can never change. Yeah, they're tied together. The reactions of products are tied together. That's probably the best way to say it. So increasing and decreasing, you can think of it as Q. And if you want to think about it as reaction quotient versus K, that's one way to think about it. Okay. But there are other things that you can do to the reaction here. You can add heat, or also known as increased temperature. Okay. Both those mean the same thing. Now, temperature is in this reaction in terms of your kilojoules, your heat. So if I add heat, essentially I treat it like a reactant, okay, or a product. And so in this case, it's a product, so it's going to cause a shift to the left because I have too much heat now, and I've got to use up some of that heat to make reactants to restore the balance. Okay. And if I remove heat or lower the temperature, that causes a shift to the right. Now, I do want you to star the temperature ones because temperature is a very unique situation here because temperature causes a shift, but temperature is not in the expression. So it's causing a shift without being included in the expression, which means these change the K value, whereas nothing else changed the K value because every other situation has something that's within the K expression. So those can balance each other out and restore back to the same K. But temperature is a factor that's not included in the expression that's causing a shift. So that shift can't be compensated for in the same way as other things. Yes, Andrew.
On that bottom where you're removing heat, if there is a reverse shift, you can also remove slightly increase the heat as well.
Yes, I would say that. But
like overall.
Yeah, I wouldn't worry about that arrow changing like that. But you're right. It would make a little bit of heat to replace the heat that's lost. Yes. So you do need to remember that when you add or remove heat or change the temperature, the K does change. It's the only factor that changes K. Okay, only factor. Everything else, K stays exactly the same except for temperature. And the way a reaction responds to temperature change actually tells you whether it's exothermic or endothermic. Because in this situation, in this reaction, if you increase temperature, it shifts to the left. That means this is an exothermic reaction. Okay, because K decreases as temperature increases. Because the denominator is getting bigger, it's shifting to the left. Again, not something you have to memorize, but it's something to think about here. Because if temperature causes the reactants to increase, then your K value will decrease. So if you see two K values, and as the temperature goes up, the K value goes down, you can make an assumption that, oh, the heat must be on the right because I'm making more reactants when I increase the heat. Questions about that? Okay. Two more factors here. Okay. One, pressure. Okay. Pressure does not have a specific direction in which it goes, like for every reactant or product. What you're looking at here is moles of gas on each side. Okay. And when you increase pressure, it shifts to the side with less gas molecules. So in this case, on this side, we have 4 gas molecules, and on this side, we have 2 gas molecules. And it's important you say the word gas. It's not all the molecules in the expression, it's just the gas molecules. Yes, the IB will take points off as well. That's one of those nitpicky things because saying just molecules includes solids and liquids, and those aren't factored in there. Like there was also a multiple choice question where I did that as well. I made one of the choices where the coefficients added up to the same on both sides, but there were solids in there, and the other side it didn't add up to the same, but only if you looked at the gases. And so like I think let me see, I think I can pull it up. Hold on a second. Let's see. Where's my Dropbox? Where's my Google Drive? Like then that's the side with fewer gas moles. 0 still counts as fewest. Correct. Yes. I think I have it in here. Let's see. Oops. Oh, what the heck? Where'd it go?
I feel like the best way to think about it is collision theory, right? If you increase the pressure on the side.
Yeah, more collisions happen, so you're gonna go to the side with fewer. Exactly. That's one way to think about it. Where did I put the test? Oh, so I'm like, I guess maybe this one. Because back then we had blocks and stuff like that. This one, did I change this one? No, that's not the one. I had one like where I made it. No, it's top of 10 though. What? Why does it keep going toward that when I don't want that? I'm trying to find out. Is it in my Dropbox? Hold on a second. Sorry, this is not really good recording, but whatever. They can sit through it. They're not here. Yeah, they can skip around. Skip about a minute ahead from what I'm talking right now. Yeah. Oh yeah, here we go. This was y'all's test and stuff like that. But so what I had here was you see if you're not paying attention to coefficients, you might think that B has the same coefficients on both sides because there's 2 reactant molecules and 2 product molecules. The catch is though, one of these is liquid. So it's not really 2 and 2, it's 1 and 2. Up here it's 5 and 4, but it's really 4 and 4 because the liquid doesn't count. So again, a student that just thinks, oh, if the coefficients are on both sides the same, that there's no change in pressure, makes a mistake here. That's again knowing the extra layers of the information to minimize mistakes. And so here is understanding that it's only gas molecules we're counting. And so if I'm the IB, I make this question like this to make sure that a student fully understands the question and only gets it right if they fully understand the concept, as opposed to just half understanding or trying to find shortcuts for it. And so A is the correct answer. It's not affected by pressure because there's 4 gas molecules on the left and 4 gas molecules on the right. And you have to say gas molecules in your explanation. The Chatelier's principle is a very explanation heavy thing. They'll give you an equilibrium and do 3 parts and say, state what happens to the equilibrium position and the equilibrium constant when this is changed. And then they'll give you 3 different scenarios. Okay. So this will shift to the right. So an increase in pressure shifts to the side with less gas molecules. It's not always to the right. It's to the side with less gas molecules. Like Andrew said, if you want to think about it with collision theory, when you increase pressure, you force more collisions. Well, if you force more collisions, the molecules that are in greater abundance will collide with each other more often and make the molecules that are in less abundance. And so that, practically speaking, means that it's going to shift to the right. Last factor, okay, catalyst, okay, no effect. Because remember, a catalyst speeds up the rate of reaction in the forward reverse, but does not affect the position, okay? And so with this, nothing's going to change about the K, and nothing's going to change about the quantities of products and reactants, because catalyst just makes you reach equilibrium faster. It doesn't actually do anything to that. And so what I want to kind of say, and this is what I was saying about the multiple choice question, is there are 2 kind of ideas that they'll ask you about, okay? Position of equilibrium translates into asking you, which way does it shift? That's what the term position of equilibrium is. Like, which way does it shift in this case? The second one is equilibrium constant, which is how does K change? And you have to remember that only temperature changes K. So yes, they might ask you, if I increase N2, state and explain the position, the change in position of equilibrium, and the equilibrium concentration constant value, and you would say the equilibrium constant value does not change, but an increase in N2 will cause a shift to the right toward the products. So you definitely want to address both these things. And again, please read questions very carefully, because I think I saw a lot of students kind of skimming through questions and missing things. And the IB is not as generous in bolding as I am on some of the questions. I don't think they bold a lot of stuff in there. So you have to read the entire question, and if it asks you to draw a name, you make sure you draw and name everything. Okay. So I had a few kids not name stuff in problems because they just weren't paying attention to the question. And those marks, you're gonna lose. Okay. So those are the main ideas of standard level equilibrium. So understanding, 1, what a dynamic equilibrium is. 2, understanding what the graphs of equilibrium are. These 2 graphs that are different in how they define equilibrium. 3, understanding how to write an equilibrium constant expression, understanding how to plug values into the equilibrium constant expression, and what the K value means. 4, what does Q mean in relation to K conceptually? And then 5, the Chatelier's principle. How do different stresses affect which way the reaction shifts, and which factors actually change Q and which factors don't change Q? And again, temperature is the only thing that affects, K, not Q. Only thing that affects K in the equilibrium. Everything else changes the values so that you go back to the same K. It's just a different ratio to get the same value. Okay. Questions? Okay. I'm going to pause there for SL, and then we will resume in a couple minutes for HL. Okay, so for higher level, there's two major ideas here that you need to focus on. One is solving rice charts, okay? And just a reminder, the rice chart is designed for reaction, initial, the change, and equilibrium. So a rice chart is designed this way to organize the information in several rows of material, okay? And for equilibrium, everything needs to be in molarity in this system, okay? So you want to calculate everything in molarity and then plug it into this rice chart, okay? So for example, if you have like H2 plus Cl2 yields 2HCl for your reaction, what you need to do is organize this and organize the information you're given to kind of figure out what piece of information that you have in the problem. And each setup, each problem may have different information that allows you to solve for different things in the scenario. So there's kind of the simple scenario to the hardest scenario. Okay, the simplest scenario is when you have all the equilibrium values. Because if you have all the equilibrium values, you can solve directly for K. So knowing all the equilibrium values allows you to solve for K directly. So that's the most basic way to calculate. Okay. Now, if you have the initial values for substances and then one of the equilibrium values for this, then you can finish the rest of the chart by using the change row to calculate all the other spaces. Okay. Now remember, change is based on the coefficients. Okay. So we establish it as x as 1 mole and then 2x as 2 moles. Now notice I didn't write signs in there because it really depends on what you start with to determine which way your signs are going to go. If you start with H2 and Cl2, then those sides will be minus and then HCl will be plus. If you start with HCl, then that side will be minus and the other sides will be plus. In an equilibrium reaction, like I said earlier in SL, it doesn't matter what you start with, reactants or products. The reaction is written in the way it's intended, and you plug in the values exactly that way. Don't go reversing the reaction because you started with HCl instead of H2 and Cl2. It's the same reaction, you're just plugging different values in. So you can start with 100% HCl and then have to make H2 and Cl2 to reach equilibrium. So don't be fazed by that in the scenario. Okay. Now, the third scenario is you have only your orange lines. You have just initial values, and that's where it becomes a little bit more challenging, okay? Because when you have initial values, and I'm going to set up a problem here. Let's say we have 4.0, 4.0, and 12.0. Actually, we'll say 0 here. And we know K is equal to 25. Well, we know our X here is minus X, and plus 2X because we have no HCl, so that side has to be positive. And in these rice charts, if one thing on one side is negative, then everything on that side is negative. And if one thing is a positive, then everything is positive. And so when you're doing the rice chart here, you get 4 minus X, and then 2X as your totals. Okay. And once you do this, you realize that you have all the equilibrium expressions and that you have K is 25. Well, K is equal to HCl squared over H2 times Cl2. So now that you have expressions for each of your substances at equilibrium, you plug those values in. 25 is equal to 2x squared over 4.0 minus x squared. What is unique about this scenario? What do you notice once you plug these values in? You can take the square root of both sides. This is an example of a perfect square. Now, k doesn't have to be a perfect square. I'm just doing it as a perfect square because it's easier for me to calculate. But k doesn't have to be a perfect square. But if you have a square on the top and a square on the bottom, you can square root both sides to solve this equation. So this becomes 5 is equal to 2x over 4 minus x. So we calculate 20 minus 5x is equal to 2x. So 20 is equal to 7x. So x is equal to, what is it, like 2.857, I believe, for x. Yes, Alexander. Well, no. You have to be careful. This is one way the IB does it to make it easier so you don't have to do quadratic correct. But there is the 5% rule, which we're going to talk about in a second. So both these scenarios are possible. But the 5% rule comes up when you don't have a perfect square on both sides. So you're right. I think it's important with Rice charts, especially in HL, it's all about the setup. Putting all your values into your Rice chart and seeing, okay, what do I have? What do I not have? What can I solve for? And then set up the expression and plug stuff in, and it will all work itself toward the answer. And so if you see there's a square on top and the same thing on multiplied on the bottom, then you have a perfect square, square root both sides. Okay? And then solve for it. If you don't have a perfect square, then k's got to be very, very small, which means then you can use the 5% rule to calculate that, which we're going to talk about in a second. But x here is, I think, about 2.857, because I think that's what 6/7 is. And so this becomes, for a final, 4 minus 2.857, which is 1.143, and then this is 5.714 for your equilibrium values here. Okay. Generally speaking, do these values make sense for this problem? Do these values make sense for this problem? Okay, why, Lucia? Because if you're taking if the equilibrium is method on the right, if you start like that and you decrease on the right and decrease on the left. Okay, that is true. You have an increase on the right and a decrease on the left. You have no negative values? Well, yes, you also have no negative values. Now, tell me why these answers make sense in terms of k. Yes? Because the bottom is smaller than the top. Yeah, so all those ideas, what Lucia said and Camila said, those are all the same ideas of kind of checking your answer. So you have no negative numbers, you have increase on the right side, and then also your k is larger than 1. So like Camila said, k is greater than 1, so you should favor the products, and your answers do have so that your products are greater quantities than your reactants. So that is kind of a general idea that you can kind of check yourself to make sure that you got it right. Because if you got a larger amount on the reactant side, then your number couldn't be 25, and then that would be a whole different scenario. So you would have made a calculator error there. It's about checking your answers here. Okay. Questions about that? Okay. Now, the 5% rule is, so this is perfect square. We call this perfect square method because you have a perfect square on the expression side, so you square root it. K doesn't have to be a perfect square, like I said. You have a calculator, you can use it. Okay. The other manner of solving these Rice charts is where the IB will tie this into acid base, and usually this has to do with weak acid, weak base reactions, where you have something like this, a weak acid or a weak base reacting with water to dissociate in an equilibrium expression. And so you'll see something like Ka is equal to, I believe, 7.2 times 10 to the negative 4 here. K is very small. So if you start with an amount of reactants, your amount of products will be very, very small. So you can make some assumptions. And so let's say I start with 2.50 molar of HF. I will have 0 of both of these. And water I omit, remember, because it's a liquid. So what are my change values or variables here for each of these? In terms of X, what are my change values? Plus X on the right side, minus X on the left side. Because you have 0 products, so it has to increase. Do we have an ability to solve for X based on the information that's given? Like immediately? No. There's no values in the equilibrium that we can use to solve for X. So we're going to have to do something more calculation-wise. So because there's no way to solve for X, we have to carry that X down into the expression here. So it's 2.5 minus X and then X and X here. Well, our K, which is also Ka for acid base, is products over reactants. So this is X squared over 2.5 minus X is equal to 7.2 times 10 to the negative 4. So in this scenario, to avoid quadratic, because again, the IB will never require you to do a quadratic equation, you have to make an assumption. And that assumption is that X is much, much, much less than the original concentration of HF. So the amount you're subtracting from 2.5 is so negligible that we can omit this minus X from our problem. Oh, wait. I'll tell you a story after I finish recording. I don't want to be on the YouTube. So if we assume that because K is so small that the change of HF is negligible, we can make this and simplify this into X squared over 2.5 is equal to 7.2 times 10 to the negative 4. So this allows us to calculate more easily without having to do a quadratic equation. So this becomes X squared is equal to 2.5 times 7.2 e negative 4. So X squared is equal to 0.0018. We square root that, and X is equal to 0.0424 for our concentration. Okay. And so that means our equilibrium value is 0.0424, 0.0424, and then 2.5 minus that is 2.458. Technically it's 2.46, but you do get one significant figure either way, and so I'm just trying to show how they work here. And so they would take 2.458. Okay. Questions about that? Yeah, yes, Alexandra. No, you are not required to prove in the IB whether the 5% rule works or not. So I did mention that to you because in college or university, you may have to check to make sure it's valid. But in the IB, since they've explicitly stated that you don't ever have to do quadratic, you can always assume that it will work if K is small. Yes. You're welcome. Okay. So last major idea for higher level here. Okay. The idea has to do with delta G and spontaneity. Okay. We talked about this last week about in topic 15 about Gibbs free energy and spontaneity using the equation delta G is equal to delta H minus T delta S. But the IB has found kind of a thread of Gibbs free energy and spontaneity throughout several topics. So one in topic 15, here in topic 17, and then also in topic 19. But in topic 19, or 17, it becomes this equation. Negative RT ln K, because it turns out the equilibrium constant value also reflects whether the reaction is spontaneous or not, okay? And so the idea is that if I know the K value for a reaction, and I know R, which is 8.31 joules per mole Kelvin, and I know the temperature in Kelvin, I can take the natural log of the K value to solve for delta G in joules, because again, keep an eye on the units. Okay. Now, what kind of delta G do we want so that the reaction is spontaneous? What kind of delta G do we want? Yes, Lucia. Negative. So you want less than 0 for spontaneous. So you want delta G to be less than or equal to 0 for spontaneous. Okay. So if R and T are constant values that are always positive, and it's negative RT ln of K, what kind of K value would create a negative overall delta G value? Okay, what kind of K value would get you so that it would be spontaneous? Yes, Lucia. Actually, a little bit even less than that, because I didn't say greater than 1. You just have to make it positive. Greater than 1, because e to the 0 is 1, right? Yeah. So if K is greater than 1, the reaction is always spontaneous. And so this makes sense because a K greater than 1 favors products. So if you're making more products at equilibrium, that means the reaction is spontaneous. So these two things work in tandem. So if your K is greater than 1, it is implied that your reaction is spontaneous. Now, they might keep it as a conceptual thing, or they might actually have you plug in a value to solve for it. And if they do that, you have to remember that the units are really important and that R is in joules per mole Kelvin, so your delta G is going to be in joules. Whereas in topic 15, your delta G is usually in kilojoules when you calculate. So again, writing units is a huge, important factor in minimizing mistakes here. I don't want you to lose like silly marks on the IB exam because you didn't follow your units and therefore you got your number to the wrong power. Like maybe you're 1,000 times off because you thought it was in joules instead of kilojoules, and it's just easy to mix it up. So writing out your units on the paper will hopefully minimize mistakes. It doesn't completely get rid of them, but hopefully it minimizes the mistakes here. And so this unit, you're dealing with K and delta G in joules, and you may need to convert to kilojoules to get your answer. Okay. Questions about that? Okay. That is the main idea of equilibrium. Equilibrium has kind of been a shorter topic that establishes the foundations of equilibrium to allow us to go into acid-base equilibria in topic 8 and 18. And so things you want to take away from this for higher level. 1, the values that are given to you in a problem dictate what kind of Rice chart you're going to have. And so if you have all equilibrium values, you solve for K. If you have one equilibrium and all the initial values, you can solve for X without doing a complicated calculation, and you can just solve all the way down every single vertical column. If you're given no equilibrium values, now you have to resort to using X as a variable and solving for X in the expression, whether it's a perfect square or a 5% rule calculation. And then the second idea that you want to take away from this is how delta G and equilibrium are related to each other. And because of this equation that's given to you in the data booklet, you can see that K is greater than 1 when it's spontaneous. And again, this is one of those things where even if you don't remember that, you can just literally plug in values for K until you get the right idea, right? Like if you think about that and you go like, I don't know whether K is spontaneous when it's like what it is, you can literally plug in values. You can plug in 2 and you'll get a positive number, which then becomes negative overall. If you type in 1, you'll get 0. But then if you type in 0.1, then you'll get a negative natural log of K, which then makes the whole thing positive. So if worse comes to worse, then you just plug in values and see when does the sign change. Or you can just graph ln of K. I guess you should really just graph ln of K, right? Because ln of K will intersect the x-axis at 1. And so that's the way you know when the sign changes. I guess that's easier, actually, now that I think about it. Just graph ln of K and go, okay, where does the value of ln of K change signs? And that's at 1. Okay. Questions about that? Okay. Yeah, topic 717, fairly short. I'm going to stay in the Zoom call in case there are any questions, but that's the majority of it. And I'll upload this after we get off the Zoom later today. And so I'm going to stop recording right now.